Okay, so our 4 principles of design are at the top of page 911, and I don't have any fill in the blanks for those. I just have them listed. So we're going to do a couple of problems where we describe in an experiment where we see these 4 things. So the first one is comparison. Comparison is telling us that we have to have at least 2 groups to compare. We don't have an experiment unless we're comparing 2 treatment groups. You need to at least have 2. You can have more. So we just saw on the fabric problem, there were 8 treatment groups. So comparison says one of the basic principles of design is that you have to be comparing to at least 2 groups. The second one we're familiar with. You have to have random assignment. You must randomly assign your experimental units to the treatment groups. The third thing we haven't talked about much is called control. We want to control as many things about the experiment as we can. As long as we have random assignment where our experiment is valid, but to make it the best that it can be, we want to control all the other things that we can. And then lastly is replication. We want to make sure that we have enough subjects in our group so that our group actually looks like the population. So replication is kind of like sample size. The more people you get in a treatment group, the closer the treatment group gets to looking like the population. So a couple of other things that we need to be aware of as we go through and discuss these 4 elements of design. One, in this idea of comparison, we want to have a control group. So comparison and control group are related to each other. This is different than the control principle. A control group is different than the control principle. So a control group provides a benchmark or a baseline for comparing the treatments against. We want to have a control group. So there's 2 common types of control group that we can have. So number 1, we could have an experiment that includes a control group that receives no treatment, or a dummy treatment, which is called a placebo. So they receive no treatment or a fake treatment. Or your control group can be given an active treatment, but in that case, you are usually trying to compare like an existing drug to a newly developed drug. So suppose we want to compare the effectiveness of a newly developed drug for treating a serious disease with a drug that is already known to work. In that case, the experimental units that receive the existing drug are the control group. So we know that this current medication works. Let's see if this new one works just as well or better. So control group, to have the best comparison, we want a control group if we can have one. Next up is this idea of the no treatment or the dummy treatment. So that's a placebo. A placebo is a dummy treatment. That blank is the word dummy. You give it to people in an experiment so that they don't know if they have the treatment or not. So we're going to look at an example coming up where the participants in an experiment are testing aspirin's effectiveness. So we would want to divide those subjects into two groups. One group would take aspirin, the other one wouldn't. But we need to give them both a pill that appears to look like aspirin. If we don't, we can have what is called the placebo effect. And even if we do, that still kind of exists. So just to say that one more time, when we're doing an experiment, especially if you're giving somebody a drink or a pill or something to eat, you want the two things. You want the placebo and the real thing to taste and look and be exactly the same. So your participants don't know if they have the real aspirin pill or the fake aspirin pill. So along with that is this idea of placebo effect. So if you're at home watching this, pause and go watch this video. I'm going to pause our recording and play this video for the in-class kids. Studies have been done on the placebo effect. They did one with poison ivy, poison oak, poison ivy. Is that the same thing? Well, poison leaves family, okay, poison leaves. And they had people rub the leaf on their arm, but the interesting thing was they told some participants that the leaf was not poisonous, but really it was. And then they told other participants that the leaf was poisonous, and really it wasn't. And oftentimes in that study, the person reacted the way that they told them, or the way that the thing they were told it was. That doesn't even make sense, Ivani. So if you were told you had poison ivy, your body tended to react that way. And if you were told that it wasn't, your body did the same, even though what was really happening was the opposite. And I think that you have a problem in your book on that, which I personally think is really cool, that your brain can do that. So placebo effect is just when your subject is taking the placebo, but they begin to feel better or react differently because they don't know it's a placebo. Their mind tricks them because they think they are getting the real treatment. So in addition to our 4 principles of design, we have to know about control groups, the idea of a placebo, and then lastly, blindness. So whenever possible, experiments with human subjects should be double blind, which means that neither the subject nor those interacting with them know which treatment the subject receives. So whenever possible, you want the person in charge of analyzing the data to not know what treatment each subject got, and if you can, you don't want the subject to know either. That will give you the best data. Some experiments, though, cannot be carried out in a double-blind manner. If researchers are comparing the effects of exercise and dieting on weight loss, then subjects will know which treatment they are receiving. Such an experiment can still be single-blind. It can be single-blind if the individuals who are interacting with the subjects, so weighing the subjects essentially, don't know who is dieting and who is exercising. So in this case, you would probably have 3 groups. You would have a control group that was doing neither. You would have one group that was dieting, one group that was exercising, and in that case, all 3 groups know what treatment they have. There's no way to do that in a double-blind way. So 4 principles, and then these 3 elements. We are going to identify these 4 principles in our SAT prep online versus classroom course. So this is the same setup that we used when we had to walk through how we would randomly assign these students to either the classroom course or the online course. This is the same problem. So the first, well, actually, let's write down all 4 principles. This first principle is comparison. So we're going to identify the comparison in this experiment. The next one is random assignment. Followed by control. And lastly, replication. So we're going to look at all 4 principles in regard to this experiment. Okay, first one, comparison. We are comparing 2 groups. So we are comparing the online course to the classroom course. So comparison is satisfied. We are comparing 2 or more things. Random assignment we discussed at length last time. So this below then is a description of why random assignment is important. So random assignment will evenly distribute students taking an advanced math class, students with extracurriculars, and students who work. So we haven't talked much about this idea, but we always want our groups, whether it's a sample or an experiment with treatment groups, we want those groups to look like the population. And within each population, kids are different. You're going to have kids that are advanced. You're going to have kids that work a lot or have a lot of commitments after school. The population isn't all just going to be homogeneous. So what you want to try to prevent is getting a bunch of one kind of kid in a group. For instance, you don't want all the advanced math kids in the online course and then all the kids that work in the classroom course. Because then we won't know, well, was it because these kids are in advanced math? Is that why they scored higher? Or because these kids work all the time, is that really why they scored lower? So random assignment helps with that. Random assignment helps ensure that you have the same amount within each group. It's kind of like stratifying. So random assignment will help you with making sure that you have all these kinds of kids in each treatment group. So this helps ensure that effects of other variables, such as current level of math or amount of study time, are spread evenly among the 2 groups. So it's similar to stratification. It's not the same, but it's similar. So random assignment we discussed on, maybe we should write that down, described on pages 904 and 905. So if it asks you about random assignment, unless it asks you to explain, you don't have to write this paragraph. You would just say the 50 students were randomly assigned to the 2 treatment groups. This is just explaining why random assignment is important. Okay, next up is control. Random assignment should create 2 groups that are as similar as possible at the beginning of the experiment. But we still have, or we must still control variables that could be confounding. So we want to control all the things that we can. We can't control what math class these kids are in or how much they work or whether they do things after school, but we can control that they take the same pretest and the same actual test. We can control the date that they test, the time that they test, and the place that they test. So we don't want to have some kids testing in the cafeteria that's so close to the band and madrigals and auditorium that if anything's happening in those rooms, the cafeteria kids can hear them. So we wouldn't want to put one group in the cafeteria and the other in the aux gym where you can't really hear anything. So you want it to be the date, the time, and the place exactly the same. We want the length of the class, the timing, and the content to be exactly the same. We want the teacher to be the same. We want to control as many things as we possibly can when it comes to the experiment. Do not allow personal choice. The subjects cannot choose the teaching method or the number of sessions. You have to control everything, and what allows an experiment to be valid is that you are randomly assigning to the groups, but you're allowed to control a lot of other things. And then lastly, replication. There were 25 subjects per treatment group. So a large number of experimental units helps ensure that the difference in SAT score is due to the instructional method and not chance variation. So replication and random assignment are related. Like they reinforce each other. These 2 things are related to each other. So replication is saying when you include as many subjects as you can, the closer you get to it actually looking like the population. So the more people you include, the more information you have, the closer you get to looking like the population. Then you double down on that with random assignment to make sure that the subjects you have that look like the population are then assigned to the groups and they still look like the population. You don't want to get a bunch of the advanced math kids in one group on accident and then a bunch of work kids in the other one. Okay, so that's for our SAT prep class. We're going to look at one more example that's just slightly more complicated. It's the same idea though. We're going to look at the comparison, random assignment, control, and replication. So this has to do with the physician's health study. So this was a real study that was carried out. So the physician's health study was a medical experiment that helped answer the question, does regularly taking aspirin help protect people against heart attacks? So in fact, the physician's health study looked at the effects of 2 drugs, aspirin and beta-carotene. Researchers wondered whether beta-carotene would help prevent some forms of cancer. So the aspirin was included for the heart attacks, beta-carotene for cancer. The subjects in this experiment were 21,996 male physicians. There were 2 explanatory variables or factors, each having 2 levels. So the one factor was aspirin, yes or no. The other factor was beta carotene, yes or no. Combinations of the levels of these factors form the 4 treatments. So down here you can see the 4 boxes. Then 1/4 of the subjects were assigned at random to each of the treatments. So each subject had to take 1 pill and 1 tablet every day. The treatment groups were not assigned one or both factors, that were not assigned one or both were given the placebo or a placebo. So every single person was taking 1 pill and 1 tablet. The placebo was a dummy pill, that says bill, not a dummy bill, dummy pill, that looked and tasted like the aspirin pill or the beta carotene tablet. After several years, 239 of the placebo group, but only 139 of the aspirin group had suffered heart attacks. So first, let's do a diagram so that we can see how this was broken down. So across the top, I'm gonna do beta carotene. And its 2 levels were just yes, no. Then same idea down the side, yes, no, but this time it's the aspirin. So I'm going to draw the pills to describe what happened. So in the yes box, you have 1 tablet and 1 pill, and I'm just drawing them differently so that I can tell the difference. So the circle for me is the aspirin, and the oval is the beta carotene. So the yes group got both. The yes-no got the aspirin, but a placebo beta carotene. So to indicate for me that I know that, I'm going to cross out the beta carotene. So that's how I know that's 1 aspirin and a placebo for beta carotene. Bottom left, the aspirin is the placebo. The beta carotene is active. And then the last group, both of them are placebos. So 4 treatment groups. They also tell us that within each treatment group, so 4 treatment groups, 21,996 divided by 4 is 5,499 physicians in each group. So each of these had over 5,000 physicians in the group. It's a lot of data to keep track of. And at the end, the results were that from this group, 139 had heart attacks. And in the bottom right-hand group, 239 had heart attacks. So what we can see here is the physicians that took aspirin had a lot less heart attacks than the physicians that did not. So 100 less heart attacks for the group that took aspirin. Where do we see our principles come into play? So, number one, researchers are comparing in this case, two treatments. So it's the ones that I have highlighted in color. They're comparing aspirin to no aspirin. And then this blank is placebo. Okay, the next box, researchers randomly assigned each subject to a treatment group. So did we have comparison? Yes. Was there random assignment? Yes. This next box is control. So the researchers controlled the gender. So these guys all had the same gender. They were all physicians. They all had to take one tablet and one pill. And then lastly is the idea of replication. There were over 5,000 subjects per treatment group. This number of subjects helps ensure that the difference between the groups is due to the aspirin and not just chance variation. Not just that one group had a lot of healthy physicians and the other one didn't. Or not just that one group had a lot of athletic physicians and the other one didn't. So replication helps us know that it's the aspirin that caused the change and not some other confounding variable. So the problems that come after this then, just want you to identify, a couple of them want you to identify the 4 principles. And then I think one of them wants you to choose which plan sounds better based off of whether or not the 4 principles are being followed. You okay? So that's your check for understanding to do between now and next time. And then next time is only 1 lesson.